clue.
But I was going to
All right, back to work.
quick note, if I may.
Sorry, back to work. Too much fun. So, go ahead. Yeah, all right.
Okay, for your site, I have to type in www dot to get to it.
Is that right?
Yeah, why is that?
I don't know. Is that true? I mean, if I type docjava, doesn't it like go there? Docjava.com, enter. All right.
Wow, I don't know.
Dude,
That didn't work.
it not only works, it works fast. So there you go.
Alright.
So what's a pure color? Come on, guys. Let's have a guess.
I was
color that's at like
I,
only one like wavelength, like and like so like red would be
I'm getting only one wavelength is a possible answer.
like
Yes.
a certain wavelength too.
yeah, I was
not
thinking
just-
exactly the frequency at which we have defined the color to exist at.
Yeah, I would say it would be the place where you have a peak spectral response. That would be more or less, I would call it a pure color. But if you look at it, there is some spectral response. If you go to the peak of blue, there'll be a little spectral response on red, and it looks like a negative spectral response on green. If you go to pure green, you'll see you're stimulating a little bit of the red plane. If you go to pure red, you're stimulating a little of the green plane. So as a result, I would say the only thing that will give you anything like a pure blue color would have to be something that's exactly 450 nanometers. Now, if I use what I've been using, Blu-ray, at 403 nanometers, I'm not very sensitive to that color, but it's not going to stimulate green or blue. So at 403 nanometers, it's going to look pure blue. And if I crank the intensity so that it is 100 times brighter than it would otherwise need to be, I should be able to actually see it as bright violet. So, the eye is a camera. It has a lens, it has an iris, we call that a pupil. It has a film plane, right? We call that a retina. The retina at the center has a thing called the foveus. That's where things tend to be dense in terms of the rods and cones. And then out of that comes our optic nerve. Then there's about 250,000 nerves in that bundle. We can change the focus by altering the shape of the eye. We have muscles for that. We can change the amount of light that we emit by altering the size of the pupils. We have muscles for that too. What else can we do with the eye? Oh, right. We can do pan. We can do tilt. If we want rotation, we kind of have to tilt our head one way or the other. How come we're able to see in 3D? Some people would say it's because we have two eyes, but if I cover one eye, I can still see in 3D. Right? And I can use my binocular vision system to improve my depth acuity, but that's because my two eyes are in the front. There are some animals which are called prey, where the eyes are on the sides. And there are other animals which are called predators, where the eyes are in the front. We have our eyes in the front like owls because we're predators. But if you look at pigeons, they have their eyes on the side because they're prey. They're vegetarian, you know. But there are things like hawks which come and swoop down and eat them. Pigeon hawks.
Fish that have it like on the side.
Yeah, I think some fish have eyes in the front. You know, there are some fish that have eyes on the side, right?
What are iguanas? Are they prey or predator?
Iguanas. I don't know.
your eyes.
Isn't everything
There,
like a
there's
predator to something else? More or less.
is everything you mean like a
Like
pigeon
deer.
is hunting corn?
Yeah. No, but like a frog eats an insect,
The
but like
circle of life.
a snake eats a frog or something.
With a circle of poop, right? Because things that poop it goes into the ground where the grass grows and the cows eat it, and then they make the milk, and then we eat the cows, and then that makes more poop. It's the cycle of poop. So I think I got that from South Park. So so there's this. It was Mr. Hankey who was saying. So it turns out there are these ways in which you can see in 3D if you're a pigeon, and the way you do it is you bob your head forward and backward. So pigeons, when they fly, they're always moving their heads back and forth, and when they're walking, they're always moving their heads in and out because they want to see multiple views, and so they're able to extrapolate 3D. You probably didn't know about the cycle of poop either. So there's lots more rods and cones than there are fibers leading along the optic nerve. There's only 250,000 fibers or nerves in the optic nerve bundle. So what happens inside of the rods and cones is we're able to use neural tissue in order to be able to extract signals. And that neural tissue does low-level pre-processing inside of the eye. The macula can detach from the retina, and that can often happen and cause blindness as people get older. This is adult onset macular detachments. So this is a medical condition. Sometimes it can be reattached, sometimes not. Usually there's some laser involved. There is fluid inside of the eye. Oftentimes that gets clouded and has to be drained and refilled, especially as people get older. In the lens of the eye, people get such things as cataracts. These can often be removed, and lenses can be replaced. And there are all kinds of interesting and wonderful eye surgeries that can occur. There are also biomedical imaging devices which allow us to range to the back of the eye. Min Su, for example, works in an area called optical coherence tomography. Tomography means to take slices. And so what he does is he uses what is the moral equivalent of a Michelson interferometer, and he ranges deeply into the back of the eye. And this is what people do in ophthalmology. They are able to range through the vitreous fluids inside of the eye and down into the back of the eye by a couple or 3 millimeters using an infrared wavelength. So at the end of the day, when we think about the eye, I like us to think about a camera. And as a matter of fact, I like to think about it in terms of a digital camera. And when I think about the optic nerve bundle and its 250,000 nerves, I also like to think about the rate at which the nerves can fire, because that gives me an absolute bandwidth out to the visual cortex. And that bandwidth is typically constrained by optic nerve retention time. The synaptic retention time runs around 12 hertz. So when I figure 12 hertz times 250,000, do they have a calculator here? Calculator, yes. So here's a little computation you can do. 12 times 250,000 is going to give me 3 million bits per second. 3 megabits per second worth of signal out of the optic nerve. Multiply by 2, I suppose. What's USB? USB 2, rather. USB 2 is 480 megabits per second, isn't it? So it's not a particularly fast camera. So when we look at the eye, we can see there are a density of cells in the back of the eye, and that density changes as we move across the fovea. The fovea is the place where the optic nerve meets the cornea from the back. And rods and cones are different in their sensitivity to different levels of light. So one is much better in low light conditions, such as rods are better in low light conditions than cones. But in high light conditions, the cones are much more sensitive. I find that what happens as a result is when things start to get dark, I lose the ability to sense light. It's much harder to sense. When things get dark, it's harder to sense color. Yeah. When things get dark, it's harder to sense light. Yes, of course, that's true. But when things get dark, it's harder to sense color. So you don't see color very well in the dark. And let's see.
Just a random one. How does night vision work?
Night vision. Night vision works because it's illuminating, usually with some sort of infrared source, or is using the infrared sources passively. Usually it gives you an artificial color of some kind. Sometimes night vision goggles they illuminate in green, for example. So what have we seen now? The signal gets transmitted to the brain. We get color difference component being transmitted out. So it's R minus G, B minus Y, and R plus G. I've seen color difference component used in communication systems as well. You can find it coming out of some video cassette recorders, what they call Betamax machines. They give us color difference components. Humans are very sensitive to brightness changes, not as sensitive to hue and saturation, and this gives rise to band limits that are inherent in the NTSC system. So when they use the IYQ system, Y has been allocated about 4.5 megahertz of bandwidth. The in phase is about 1.5 megahertz of bandwidth, and the quadrature is about 0.5 megahertz of bandwidth. By band limiting the different components, they're taking advantage of the inherent limits of human perceptual color. So they have come across I'll call it a perceptual coding system that allows them to give you reasonably good-looking images that have been band limited. And I guess we've seen enough of the tri-stimulus color diagrams to satisfy us. Here you can see brightness is being equated with value. So as you go up the color cone of the hue saturation value system, you can see how saturation is the magnitude of a rotating vector that rotates about the hue. The value, as it goes down, will tend to make things darker, and as it goes up, it makes things brighter. And there's the RGB color cube again. So let's zip through some of these slides because I think there's too many of them. and talk a little bit about color quantization, which is the subject of your midterm. So what happens when you have a 16-bit DICOM image and you want to display it on an 8-bit color display? Right, the DICOM image is grayscale. Right? A grayscale image in the RGB color system has equal values of red, green, and blue. So when you have equal values of red, green, and blue, and you take them together down to 0, it makes a black area, and when you take them up to 255, it makes a white area. And so then if you look at the DICOM image and you say, but gee, it gives me a dynamic range that's 16 bits. What can I do to convert a 16-bit image into an 8-bit image? The answer is requantization. You have to requantize the image in order to be able to alter its dynamic range. So what's that about? What's this requantization really about? And color requantization is one of those things that allows us to work with color images, but we can do this with grayscale images as well. Let me give you a practical demonstration. Oh, that's done. If I use my little image processing program, j2d.gui.main, that took long enough, didn't it? Open. Let's open a color image. Color. What shall we open? Let's open the kitten. Oh, I know. Let's open something colorful. Let's open peppers. Yeah, they're nice and colorful. I got red, green. I don't have too much blue, but I got enough colors to mess about with. Now let's do color quantization, and let's try median cut algorithm. So color quantization to 256, 128, 64, 32. Can you start to see a little distortion here? Here's 4 colors. Here it is back at 256. That's color requantization. There are lots of different algorithms for color requantization. Here's another one. Here's the linear cut. So now we'll just cut everything but the most significant 6 bits, 5 bits. Cut 1, 2, 3. Oh, we're cutting from the back, I guess. Here we'll cut all 8 bits. There's nothing left. So that's kind of fun, right? You could say, aha, this is a naive algorithm. It doesn't work very well, but it's very fast. Let's find another one. Color quantization. Here's an octree. Haven't tried this in a long time. Oh, that works. Doesn't look so good, but it works. Ooh, nasty. Here, 8 colors. So that's a 3-bit image, right? The Crayola crayon concept of color. In fact, if you know which colors you want, you can just map the colors directly to those colors. So there's a color filter here which will do safe colors. Those colors will be safe for an RGB color system. that is used for NTSC transmissions. So you can use those colors in television, for example. There are certain colors that are called web colors, which are always available on any browser. And those are defined by www consortiums. So color quantization works real good with color images. What happens if you have a grayscale image? Very glad you asked. Actually, you didn't ask. Well, let's see now. I've got a knee. Here's a knee. Kind of looks knee-y. Knee-y. This is a very strange class because the professor keeps showing his knee. Yes, it's true. So now we'll try octree color quantization with a grayscale image. Is this like working? I guess it is, yes. So it does work. We'll try linear cut on a grayscale image. We'll try this Wu algorithm, whatever that is. I read about it in one of them journals. One of them academic journals. And here's median cut algorithm, whatever that means. So, apparently these color quantization algorithms work reasonably well. They allow us to requantize an image, even a grayscale image. But so far what we've been doing is we've been taking an 8-bit image and requantizing it to fewer than 8 bits. So what happens if we take a 16-bit image and try and requantize it to an 8-bit image using one of these algorithms? That's the midterm. Now we're getting somewhere. So let's get this out. Oh, and by the way, if we go back to, let's see. Oh, that's nice. Look what that did. Makes lots of dots. Let's revert to the original image, show the histogram. Then what we'll do is we'll do a median cut to 3 bits, and then what we'll do is show the histogram again, and clearly there's 1, 2, 3, 4, 5, 6, there's like 7 or 8 different colors, and they're all of equal intensity, and that's what makes this a grayscale image in comparison to what we saw from before. Moreover, I think we could do a histogram equalization now. So we'll apply the change, and there's the histogram equalization with just those colors. And apply that change and show and register the histogram. And we could say, aha, it's the same distribution of colors, but they've been spread out quite a bit. And that improved our apparent contrast. Although there's that salt and pepper noise in the image, which I believe came about because of improper requantization. Because I don't think that salt and pepper noise was in the original image. That's what I think. So, at great cost of time and effort, I have a program that can directly digest and then display DICOM images, or DICOMET images. And it's in a little package called DICOM. and it's in a little class. This is all new for you because I just put it in the software today. And it's called the DICOM file reader. And in the DICOM file reader, what I did was I set up to read a raw DICOM image, decode it, and then do a naive conversion. And here it is when displayed straight from a 16-bit display, and here it is with a naive conversion. And what I'd like you guys to do is do a non-naive conversion, take this image and convert it into an 8-bit image using median cut algorithm. Aha, you say. And what is median cut algorithm? Good question. So, let's think about what it is we're going to try and do. I'm going to take a 16-bit image and make an 8-bit image, which means I'm going to take something that has 65,536 different possible grays and turn it into something that has 256 distinct grays. How will I know which grays are appropriate? And how will I know how to map the colors, or let's say the grayscales, into the new grayscales? And you can use color quantization on grayscale images and still call it color quantization. Sorry, is there a question?
You said you could take it on a gray image.
Yeah, gray is a color. I consider black and white to be colors in the most general sense. And variations between black and white are still considered colors. Gray is a color. It just happens that it's equal amounts of red, green, and blue. From a computer programmer point of view, it's just a number in color space.
What's
Clear?
clear?
I don't know. You mean, is clear a color? Is this a trick question? It's like, this is an actual question? Let me cough while I think about that. I don't know. I don't know what color clear is. If you were going to try and model something which is clear in a computer graphics program, you'd be identifying a material property which would be called glass. Its transparency would enable it to take rays and move them from one place to another, and you would describe it with an index of refraction, and you would describe it with a coefficient of speckle, and you would have the ability to do diffusivity, and you could get highlights. So if you're trying to model glass, it's a material property that you would imbue into the computer graphics program. From a physics point of view, it's just something that transmits rays. It doesn't have an inherent color on its own, but glass can still have material properties. So those material properties can include the ability to refract rays of light. So I'm not sure if I'm answering your question. What color it does? It appears as though it takes on the color of whatever's behind it. How's that for an answer? I mean, if you wanted the invisibility cloak, what you would do is you would make it so that it appeared to the outside world as though it were transparent. It would show others what the image looks like behind you. So if you put a display on your in your clothes that looks like video, and then you have a camera in your back, then when I stand before you, what you should see is behind me. And then it would look as though I'm transparent. And that would be like my invisibility cloak. Right? So I mean that's key. it takes the light from behind me and transmits it so that it's in front of me. So I would have the color of whatever the wall is behind me. You really threw me with that question. I mean, really, I'm off my game now. Holy mackerel. Okay, so color quantization requires that we identify the colors that we wish to target. We also want to be able to take the input colors and map them into output colors. If we do that, irrespective of where the pixels are, we are involved with a kind of homogeneous point processing. Right? Because we're treating all the colors the same, right? Or we're treating all the pixels the same. As long as we know what color they are, we can map them into new colors. And so we need some algorithm for mapping. So here comes the median cut algorithm. And we already know what a median is. It's the middle. And we know how to find it. We do sorting. So with the median cut algorithm, what we want to do is we want to develop a box which contains both the minimum and the maximum as limits in terms of the color range that we're going to surround with. And then what we're going to do is we're going to decide how many colors we're going to divide the palette into. So we're going to target it initially by saying, look, we're going to start with, I don't know, let's say 100 different colors. We're going to end up with 10 colors. So that is a form of color requantization. Now, if I have 1,000 pixels and 100 different colors, in the median cut algorithm, I would allocate one color for every 10 pixels. So we don't discriminate essentially by virtue of what the most popular color is. We don't say, oh, let's see what the most popular color is. That'll be the color we'll use. So this gives us a form of, I'll call it diversity in the colors that we do an assignment on. So is this a good algorithm? People seem to like it. It's reasonably fast. Are there other algorithms? Oh yes, sure, you betcha. Let's think about this a minute. Suppose I wanted to use the popularity algorithm. Popularity algorithm would be get a histogram, figure out where the maximum value is, maybe grab a couple of colors around that maximum value, map them to that maximum value, zero out the other two, and then go for another maximum value. Right? So popularity algorithm might not preserve diversity in the image. So if you have something that is like way out there, it's a very bright color, you would lose it. So maybe there's something to be said for the median cut algorithm in its ability to preserve diversity in color. So we take the color space and we divide it into a smaller and smaller rectangular box. In the case of a grayscale coordinate system, the box is in one dimension. And so then we'll tightly enclose min and max. Let's say we found colors that range between 0 and 10,000, or between 100 and 10,000, and that's quite likely, especially if we're dealing with a 16-bit image. That can go up to 65,536. So seeing a max of 10,000 is quite possible. And so when we look at the median cut algorithm and we devise the three-dimensional box, we're involved with something which is considerably more complicated than if we're dealing with a grayscale image. And so what we'll do is we'll sort all of the elements along one axis, find the median, and then we'll cut along the longest dimension of the box. That's the median cut algorithm. Then we segregate the points into the two halves. That's reasonably easy if you're dealing with a one-dimensional array, because all you're really doing is you're taking the elements in the array, sorting them, finding the middle of the array, that's your median, and then taking the array and breaking it into two halves. That's essentially cutting it into two cubes like this, only you're only in one dimension. And you keep going until you have the desired number of boxes. And then the pixels which are inside of those boxes, those colors get mapped to the average in each one of the boxes. And so here's a sample. There's 2 colors, there's 4, 16, 256 colors. Median cut. Not the greatest algorithm, but a reasonably fast one. Yes, sir.
Okay, so just to make sure I understand this, the initial box, is that the whole picture?
Yeah, it's going to be all of the, you'll have an RGB color space which borders, well, for the purpose of the midterm, we're working with a grayscale image. So you're basically looking at all the pixels, and you're going to find the minimum value and the maximum value, and that will bracket the whole array. And so maybe the minimum is 100 and the maximum is 10,000. That's going to be a one-dimensional box because of a grayscale image. And then the median, after you sort everything, will be the middle value. And then you're going to take that middle value and use that to segment your array into 2 arrays. This is a divide and conquer algorithm. And then you run it again. So you could in theory do this with a nice recursive algorithm, right? Where like quicksort, it does divide and conquer. So then here are the sorted details of sorting. The sorted. So how do you enclose the points along the longest dimension of a box? Well, here's a bunch of, I'll call them short values. Shorts because shorts are 16-bit quantities, and 16-bit quantities can range from 0 to 65,536 if they're unsigned. But for the case of when they're signed, Java views them as being minus 32,768 to 32,767, but we can ignore the sign bit when we're dealing with an image. And the shorts that we are putting in here, we have to sort them in order to be able to do our median cut. So once you sort them, I do a mat1.sort. I can show you where that's at. There's this thing, which is in the math package, and it's called mat1. And if you go to the bottom, here, I'll just type in test sort. And now you can see here's the code for the sorting. Cut it, paste it, and then if I run it, cross the fingers, and it sorts, which is just what you'd expect. So it sorts actually using a collections sort invocation, which where did this come from? Oh, I think it's part of Java, actually. It's in the collections class, Java util. Java util collections. Java util collections will sort arbitrary reference objects that know how to determine whether one is less than another. So if you take the instance of a short, which is really a wrapper around a primitive data type. This is probably the world's most inefficient sort as a result, because you're promoting all the primitive data types to reference data types and then letting the collection sort algorithm do the sorting and then converting them back to primitive data types. There's got to be I should probably have re-implemented this sort so it just works with primitive data types without having to promote them to reference data types. But I guess I didn't care. I just wanted to get something that worked quickly. Sloppy. Lazy, sloppy sort algorithm. So here's my lazy, sloppy sort algorithm. You probably shouldn't use it because it's the world's slowest thing in the world, but who cares? And it works. And that's it. And so once you have the sort, how do you find the median? Right? Here's the sort. You want the median, right? Short, median, equals, what's the median? S of S dot length divided by 2. That's the middle. The middle of the array is the median. So after you sort the numbers, you want to grab the median. That's the middle. And now if you want to know what the median is, you can print it and write something nice like median equals plus median. I can see this midterm is going to be a challenge for some. So the median is 4. Why? Because 4 is in the middle. That's the median value. Got that?
Question.
Yes, sir.
If you've got an even number of values so that there's two middle ones.
Ah. An even number of values. How many values do we have here? 11. So what would it mean to have an even number of values? Here we go. That's an even number of values. Now what happens? Does it still work? Median is 5. Is that wrong? Probably. What should it be? Should it be 4? 4.5? I don't think that there's a correct or wrong answer on this one, because you can't find an exact middle when you have an even number of items. There's no rounding here. It's just the middle. Median means middle. It's the middle cut algorithm. So you guys are going to find the middle, and there is no middle when you have a, I mean, you don't take averages between two middle points when you find a median. This is why people do convolution with an odd number of elements in the kernel, because they want to have an exact middle. You can't get an exact middle with an even number of elements. Right? If I say, here's the coffee mug, and here's the keyboard, right? What's the middle? Say, well, it's the desk. Right? Now, if I said to you, well, there's this tissue over here, and it's just to the left of the middle, and I'm like, okay, I can find an exact middle because this is a floating point coordinate system, but if I have an integer coordinate system and I put it on a checkerboard, I may or may not be able to determine whether I can get, on the Kleenex or off the Kleenex. Yeah, that's a bad example. I don't know what to say. It's a discrete system. There's no middle. So you just do the best you can. Here it's rounding it to, it's using length divided by 2. That's trunk. That's not round. That's taking, I mean, if length divided by 2 was 2.5, it wouldn't make 3. It would make 2. If length divided by 2 was 2.7, it would still make 2. So it's truncating off the decimal part because it's doing a integer division. It would still be 2. If it was 2.9999, it would still be 2. It says because that's an integer division. That's also the end of the first half of the array, because the second half of the array, when you use median cut, is going to be used recursively to do this again. What do you think of that? So this is how you do a sort. Let's see what else we can do. So the algorithm says sort the enclosed points along the longest dimension of the box. So how do you sort a 1D array? This is how you sort it. Let's see now. How do you split an array? You've got to segregate it. So you've got to split it into two halves. You want the left-hand side and the right-hand side. And so that's like, I don't know, a simple computer program that goes between 0 and length on 2, and then starts at length on 2 plus 1, and then goes to n minus 1, whatever you use for the length, minus 1.
So we just have our box is a one-dimensional.
Yes, it's one-dimensional. Yes, absolutely.
So how is that loaded? How do we load the image into that?
Ah, okay. So how do you implement this?
I mean, maybe I should just let you keep going.
Yeah, no. It's very good. So here comes the DICOM reader, right? And I'm going to give you this code. And what it does is it reads in a 16-bit image. This is a raw DICOMET image, and then and it's of my knee. And then what it does is it gets us some interesting information, data structures. One is called the file info, which will give us things like the width and the height. Also the number of bits per pixel in the image, which in this case is 16. It creates an image reader and then gives us an input stream which we feed into a decoder. That image decoder will give us an AWT image, which is an 8-bit image. But it doesn't do a particularly nice job of it. I can display the image. It doesn't look bad, but what I really want is the 16-bit version of the image, which comes from this short processor. The short processor can be passed into the short image bean, and this is how I populate the short image bean. And now the short image bean is a two-dimensional array consisting of 16-bit quantities. And now what I can do with the short image bean is I can go and get a naive image and display it. So if your question then is, how do I gain access to these images? Well, these pixel values, here they are. Here are the pixel values. Here's me setting them. If you want, you can go sib.get red and get a two-dimensional array for red. Short. Have I used R already? Yes, I have. No, I think I can do this. It's in the for loop, but it's local. So there's a two-dimensional array for red with 16-bit quantities without the distortion inherent therein. So what I can do is I can start with the two-dimensional array, or I can use the 1D array, which is just the pels right in here. And with the pels, I can proceed to use the sort algorithm. I can find the minimum. I can find the maximum. I can get the median. I can split the array. And I can get a sequence of different values using this median cut algorithm. I cannot use the median cut algorithm that I've already written because it was designed for a color 24-bit image. It was not designed for a 16-bit grayscale image. So I have to essentially re-implement the algorithm with the grayscale pixels in mind. I haven't tried actually sorting the pels to see what would happen. mat1.sort of pels. You can do that, right? Alt enter. S out, Control J, enter. Done. Let's just print done. Let's see how long that takes. I don't think it'll take very long. I really don't know. Done. Yeah, very fast. So the sorting was, I was worried that it was slow, but for the purpose of our midterm, we don't care. It's certainly very fast. Blink of an eye. Not sure why it's so fast. Okay, so that's it. That's what I have for your midterm.
I'm a little confused.
You're confused.
Yeah. A little bit.
Little bit? Should I?
Like, how do we know, like, how to map colors and stuff?
Do you want to read the book on median cut algorithm?
What page is it?
We're on chapter 13, which is on page 347. And median cut algorithm is page 362. And maybe it's a reasonable explanation. Is it the case that I shouldn't assign this until next week?
I mean, whether you assign it or not, if it's due at the same point, it doesn't really matter.
Well, I mean, I can give an extra week if you want to work on it over spring break. I got a look from Brian.
Yeah, I don't want to make that decision.
No. So the way I would do it is this. I would write it up and then go over it next week as well. So I'm not going to leave you hanging. That gives us a week to talk about it and also to read about it and then come back with lots of interesting and wonderful questions.
So just like, what do we do, like, once we use the code that you gave us, like, what would be, like, the first thing that we would need to do? Like,
You want to display the image after you're done doing the computation.
but, like, are we, with the code that you're giving us, is that already, that's just a 16-bit image, or?
Yeah, you're starting with a 16-bit image and you want to make an 8-bit image and then display it.
Okay, so we just modify the algorithm that you used in the code you're posting.
Well, I haven't written the code yet for doing the median cut algorithm on a 16-bit image. That's your job.
No, but you did it for didn't you do it for?
I did it for a 24-bit image, but it was color, so it was 8 bits per pixel. So now you got to do it for a 16-bit image where there's only 16 bits per pixel and it's grayscale.
So what is this DICOM code that you're?
Oh, the DICOM code lets you decode the input file and makes a 16-bit image out of it.
So we get.
You get the DICOM code. You get a 16-bit image. Now you got to make an 8-bit image.
So I'm still not sure, like, when we get the image from your code, how do we put it into the short array?
I give it to you in a short array. It comes out in a short array.
So you're giving us the array that we need, and we just have to implement the actual.
Exactly right. That's exactly right. So, I'll call it the midterm assignment. Oh, how clever. And then what we'll do is we'll say, given a DICOM 16-bit image, write a median cut algorithm implementation in the language of your choice, Brian. Are we going to see Ruby soon? That outputs a 8-bit image and displays it on the screen. And that's it. And it's due in 2 weeks. Due dates. Due in. That's before the spring break, right? The 20th? Yeah. Okay. And that's when it's due. And we'll hit submit. And if we need to revise it later to make it more clear, I will do that. I'll also make sure that the code is uploaded so that you all can get to it. And this video, of course, will be uploaded as well.
Is the PowerPoint going to be on?
And the PowerPoints are in the video.
Yeah, but like, is there a way so we can just look at the PowerPoint?
I
It's a
don't
lot
know.
faster to just look at a PowerPoint than
And to look at the videos?
Than skim a 2-hour video and like
Oh.
have to be at your pace with how we look through. You know?
It may be the case that you can advance through the video, but I'm not sure.
Okay. There's no way to just upload it?
I should be able to.
Yeah, you should.
I think I can. I haven't thought about it. Let me do that offline rather than doing that during class.
Well, yeah. No.
Yeah, let's not do that right now. Okay, have a good evening. Stay warm.